In order to find the reaction forces at the support of the bridge frame, which consists of three parts and it's held together with a pin support at point A, D, and E, while a rocker support is present at point C and F, and a roller is present at point B. In order to determine the horizontal and vertical components of reaction of all of these supports, we have nine unknowns. So we won't be able to apply our equilibrium equation on the whole frame one at a time. So in order to solve this problem, we have to break it into its individual segment and apply the equilibrium equation to solve for those unknowns. So let us first consider segment BD, which has a roller support at point B and a pin support at point D. So let's go ahead and draw the free body diagram. Now for the roller support, I have just one unknown going vertically upward, and it is restricting the motion along the vertical direction, whereas for a point D, we have a pin support. So we have support reaction both in the X and Y direction. Next, the external load of uniformly distributive loading is applied on the span of 30 feet. So we can convert this distributive loading into point load by multiplying 2 kip per feet into 30 feet. That gives us a point load of 60 kip. Now this point load will be acting at the centroid of this distributive loading. Since it is a rectangular loading, it will be acting in the middle of that span of DD, that is 15 feet from point B and 15 feet from point D. Now, once we have our free body diagram, let's go ahead and apply our equilibrium equation. So I'm going to start with summation of moment at point D because it will eliminate my dx and dy, as these two forces won't create any moment as they are passing through the point line of action. So we have our by that is going in the upward direction and have a moment arm of 30 that is going to create our clockwise moment, whereas the 60 kip force pointing downward is going to create our counterclockwise moment with a moment arm of 15 feet. Simplifying, we get our value of by as 30 kip. Next, we can apply our summation of forces along the horizontal x direction. In this case, we just have one force acting along the x direction, that is dx. So the value of dx is equals to 0. Finally, let's apply summation of forces along the vertical y direction equals to 0, taking forces pointing upwards as positive. So I have my by going upward direction of 30 kip, and then I have 60 kip going downwards plus dy. Simplifying, we get our value of dy as 30 kilopounds. Now, once we have these forces, let's show them on our diagram here as well, so that we know when we are considering the falling segment what will be the direction of loads that will be acting on those segments. So here by is pointing upward, dx is 0, and dy is also going in the upward direction. Now, let's move on and consider our second segment of A, B, and C and develop its free body diagram. Now for the free body diagram, point A is a pin support. So it will have two reactions, one along the horizontal direction given as AX, while the other one will be in the vertical direction as the motion is restricted along the horizontal and vertical direction of a pin support. Next, I have our rocker arm that is present at point C. And for the rocker arm, the horizontal motion is allowed, so we won't have any support reaction. However, the vertical motion is restricted. That's why we have a single support reaction of Cy, that is at a distance of 5 feet from our point A. Next, I have the roller. Now, in this case, since the roller value, we have actually calculated By of 30 kilopounds going in the upward direction for the segment BD. Since this segment is connected with the segment ABC, once these two members are connected, the force should cancel out as these are the internal loads. So in order for that thing to cancel out, our By will have the same magnitude of 30 kilopound, but this time it is pointing downwards. So it will cancel out the upward 30 kilopounds once these two members are connected. Finally, I have our distributive loading of 2 kilopounds per foot. Here we have a span of 15 feet. So multiplying 2 by 15, we get our 30 kilopound acting downward. That will again will be in the middle of our rectangular section of 7.5 feet from point A. Now, once we have our free body diagram, let's apply our equilibrium equation. Now, starting with summation of moment at point A, since it will eliminate our AX and AY in the expression, as those two forces won't create any moment, we have our CY going upward with a moment arm of 5. This is going to create our counterclockwise moment. That's why it is taken as positive. Next, I have our 30 kip force pointing downward with a moment arm of 7.5. This is creating our clockwise moment. So that's why it is negative. And our By is also going to create our clockwise moment. Simplifying, we get our value of Cy as 135 kip. Next, let's go ahead and apply our summation of forces along the horizontal direction. In this case, I have just one force acting along the horizontal direction, that is Ax. So our value of Ax is equals to 0. Finally, let's apply summation of forces along the y direction equals to 0. So our AY is pointing upward, that we still don't know the value. So let's give it a variable plus 135, that is our CY going in the upward direction. And then I have my BY going downward, as well as the distributive load converted into a point load is going downward. Simplifying, we get the value of AY as negative 75 kip. Now here the negative sign is indicating that the direction that we pick on our free body diagram, the actual force is in the opposite direction. So representing them on our diagram, our AY is pointing downward of 75 kip, AX is equals to 0, whereas CY is going in the upward direction of 135 kip. Now let's move forward to our final segment of DEF and develop its free body diagram to figure out the support reaction at point E and point F. Now for the point F, again it is a rocker that is present there. So the motion along the horizontal X direction is allowed, whereas the motion in the vertical Y direction is restricted. That's why we will just have one reaction force acting in the vertical Y direction given as Fy. Whereas for point E, since it is a pin support, we will have our both support reactions of Ex and Ey, as the motion along X and Y direction is restricted at point E. Next, we had our pin at point D. Now, since this segment connects with the segment BD and the reactions are the internal forces at point D, since once they combine together, they will cancel out. So our DY direction should be going in the downward direction of 30 kip, where DX was equals to 0. So finally, let's convert our distributive load into point load again. So 2 times 15 feet give us the point load of 30 kip that will act at the centroid of that rectangular section, that is 7.5 feet from point D or 7.5 feet from point E. Now, once we have our free body diagram, let's go ahead and apply our equilibrium equations for the segment DEF by starting with summation of moment about point E equals to 0, taking counterclockwise as positive. Now, once we are doing that, starting with our dy going downward with a moment arm of 15 feet, that is creating our counterclockwise moment. Similarly, our 30 kip point load with a moment arm of 7.5 is going to create our counterclockwise moment. That's why those two are taken as positive, whereas Fy going in the upward direction with a moment arm of 5 feet is going to create our clockwise motion. That's why it is negative. Next, Ex and Ey won't create any moment as they are passing through the point E. Simplifying, we get our value of Fy as 135. Okay. Next, we can go ahead and apply our summation of forces along the horizontal x direction. Again, in this case, we just have one force acting along the x direction, that is Ex. So the value of Ex is equals to 0. Whereas once we apply our summation of forces along the vertical y-axis equals to 0, taking forces pointing upward as positive, I have my dy value of negative 30 as it is pointing downward. Same case of the point load of negative 30k, whereas our Fy is pointing in the upward direction. So that is plus 135 plus Ey equals to 0. Simplifying, we get our value of Ey as negative 75k. Now again, here the negative sign is indicating that the direction of Ey that we have picked on our free body diagram, the actual force is in the opposite direction. So it should be pointing downwards.